We can now move on to section 6.3, which covers Taylor and Maclaurin's series. So all the series we have done so far, we were able to make it look like a geometric, right? Which made it not very hard. However, think about it just really quick. It's actually very rare it will actually work out to where I could do that because there are functions everywhere that there is no possible way to make it look like geometric, right? Like the function sine of x. You know what I mean? There's no way to make that look like a over 1 minus r. There's no way. And there's a bunch more. That's just the first one I thought of because I saw it right here on my note sheet. But so what do I do in a case where I can't make it geometric? This is what I do. Okay, so now we are going to focus on these, which is going to help us do some that cannot be written geometrically. So let's define what a Taylor and Maclaurin series is, or what they are. If f has derivatives of all orders at x equal to some a, they will tell us what the a is. Then the Taylor series for the function f at a is equal to the sum of the nth derivative of a divided by n factorial times x minus a to the power of n. So if I plug 0 in first, that's just f of a over 0 factorial times x minus a to the 0, which would simplify down to just f of a. Plus, then plug in n equal to 1, the first derivative at a over 1 factorial times x minus a to the first, which would simplify down to f prime of a times x minus that a. Again, they are going to tell us what a is. Plug in n equals 2, f2 prime of a over 2 factorial times x minus a squared, which would give me f2 prime of a over 2 factorial, which is 2. 2 times 1 is just 2, times x minus a squared. And then I would keep on and on and on forever and ever. The Taylor series for f, where a is equal to 0, is known as the Maclaurin series for f. We like these because a is just equal to 0, so there's not as much work of having to make sure I put x minus a number squared, that kind of thing. And the theorem I have is that if a function f has a power series at a that converges to f for some interval containing a, then that power series is the Taylor series for f at a. So this is how I find what the power series is if it's not geometric. I do this. So notice here these terms will just go on and on and on for all time, right? For the purposes of our class, just assuming they go on and on and on, doing that a bunch of different times is a lot. So all I want to make sure is that you understand it and can list out the first few terms instead of trying to list them all out. So for that reason, we have this guy. If f has n derivatives at x equal a, then the nth Taylor polynomial for f at a is equal to, and it's the same exact thing I have here, it's just the first n terms. So if I ask for P2, I'm going to go up to F2 prime. If I asked for P8, I'm going to go up until F8 prime. That's what I mean. The nth Taylor polynomial for f at 0 is known as the nth Maclaurin polynomial. So again, if the a is going to be 0, it's going to be the Maclaurin. Okay. All right. Example number 1. Find the Taylor polynomials P0, P1, P2, and P3 for the function natural log of x at x being equal to 1. So I'm actually going to change it up a little bit. This is what the book said, I don't really understand why they asked for P0, P1, P2, and P3 whenever in order to get P3, you have to do all of these. So we're only going to do P3 because the rest of them are a part of that. Okay, so P3 for f of x equal to the natural log of x at x being equal to 1. Okay. I'm going to write it down just so that we don't get confused. We are looking for P3 for the function natural log of x at x equal 1. So us asking for P3 means we want up until the third derivative, okay? So the function is natural log of x. So let's find the first derivative. The derivative of the natural log of x is, of course, 1 over x. Then find the second derivative. The derivative of 1 over x, we could use the power rule or the quotient rule, whatever you want to use. Since this was a calculus 1 thing, I'm going to assume you know how to do this, but if not, let me know. I'll just let you know the derivative is negative 1 over x squared. P3 means I have to go all the way to the third. The derivative of negative 1 over x squared is 2 over x cubed. There we go. Okay, and then for the Taylor series stuff, what I want is all of those at my point A. So plug in A, plug in A, plug in A, right? So our A here is x equal to 1. So I'm going to plug in a 1 to all of these. So f of 1 is the natural log of 1. The natural log of 1 is 0. F prime at 1 is going to be 1 over 1, which is 1. F double prime at 1 is going to be negative 1 over 1 squared. 1 squared is 1. 1 over 1 is 1. So it's negative 1. F triple prime at 1 is 2 over 1 cubed. 1 cubed is 1. 2 over 1 is 2. So P3 is going to be equal to, we always start with just, again, I'm looking at the formula right here, right? So for the first one, plug in 0 here, which just means I want f of 1 over 0 factorial times x minus 1 to the 0, which gives us just f of a, which is just f of 1. So first term is 0, plus, for the second term, f prime of a times x minus a. Well, f prime of a is equal to 1, so it's just 1 times x minus a. We said our a was 1, so that's just 1 times x minus 1. Plus, for the next term, it'd be f2 prime at a over 2 factorial times x minus a squared. Well, f2 prime of a, we already said was equal to negative 1. So we can put minus 1 over 2 factorial is 2 times 1, which is just 2, times x minus a squared. So x minus 1 squared. Then do the next term, which is my third term right here. f3 prime of a, which we said was 2, in factorial, which is 3 times 2 times 1, which is 6, times x minus 1 cubed. And that's it. I would be fine if you stopped right here, but technically speaking, 2 over 6 would be better written as 1 over 3. So if you wanted to be particular about that, 1 times x minus 1 is just x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed. But if you are in my class and you want to just submit that, I'm okay with that. I just want to make sure you understand the process. And that's it. So again, since it asks for P3, go until F3 prime, and then all of my terms are the nth derivative at a over n factorial times x minus a to the n. So just do that for every term. This one, n is equal to 0, n is equal 1, n equals 2, n equals 3, and just plug it in and see what I get. Example number 2 is looking for the same thing. It's asking, again, it says P0, P1, P2, P3. Just do P3 because the rest of them are like a part of it. So we're looking for P3 for the function f of x equals 1 over x squared at x equal to 1. So P3 means I want to go all the way to f3 prime. So start with f prime, or f of x, of course, is 1 over x squared. The first derivative, again, I'm going to assume you know how to take the derivative of this stuff, negative 2 over x cubed. The second derivative is going to be 6 over x to the fourth, and the third derivative is going to be negative 24 over x to the fifth. Make sure you know how to take those derivatives. So again, it's at x equal to 1, so plug in a 1 to all of these. F of 1, 1 over 1 squared. 1 squared is 1, 1 over 1 is 1. F prime at 1 is going to be equal to negative 2 over 1 cubed. 1 cubed is 1, 2 over 1 is 2, so that's going to be negative 2. F double prime at 1 is 6 over 1 to the fourth. 1 to the fourth is 1, 6 over 1 is 6. F triple prime of x, or at 1, negative 24 over 1 to the fifth. 1 to the fifth is 1. 24 over 1 is 24, so negative 24. And then remember, for each term, what I want to do is the nth derivative at a over n factorial x minus a to the n. So for the first term, where n is equal to 0, that's just f of a, right? Because the 0th derivative, which isn't even a thing, is just f at a. 0 factorial is a 1. Anything raised to the 0 is a 1. So this is all just 1. F at a, we already said, was 1. So for the first term, it's just 1. Now do my next term where n is equal to 1. That's going to be the first derivative at a, which we said was equal to negative 2, over 1 factorial, which is 1, times x minus a, which we said was 1, to the first, which means I don't even have to put it there. My next term is when n equals 2. F2 prime of a, we already said was 6, over 2 factorial, which is 2, times x minus a squared. Then my last term is where n is equal to 3. F3 prime at a, we already said was negative 24, over 3 factorial, which is 3 times 2 times 1, which is 6, times x minus a, which we said was 1, I messed up over there, cubed. And there's our first 3 terms. We are good. Again, for my classes, you are fine just to stop right there, but if you want to be specific, you could do 1 minus 2 over 1 is 2. 6 over 2 is 3. 24 over 6 is 4. And there we go. If any part of that does not make sense, please let me know. I would rather you ask me and get help than not get help and not understand it. Sample number 3, for each of the following functions, find formulas for the Maclaurin polynomials P0, P1, P2, P3. Again, we're just going to do P3. And then find a general formula for the nth Maclaurin polynomial and write it using sigma notation. I'm actually not going to worry about y'all doing that. I just want to make sure you understand the process, and I'm okay with that. So basically, just find the Maclaurin, which means my A is going to be 0 for each of these here. Let's do e to the x first. Find P3 for e to the x at a equals 0. So P3 again means I want F3 prime. So first start with f of x, which we know is e to the x. What's really nice about that is the derivative of e is just e. So all of them are just going to be e. Very easy. I want it at a equal to 0. F at 0 is e to the 0, which is 1. F prime of 0 is again e to the 0, which is 1, which means they're all 1. So for the first one, n is equal to 0. Again, remember what I'm wanting is the nth derivative of a over n factorial times x minus a to the n. For the first one, for n equals 0, that's just f at a. Said was 1. So 1 plus, for n is equal to 1, it's going to be 1 over 1, which is just 1. So just do 1 times x minus 0 to the first, right? Because that's what I'm going to plug in there for a. X minus 0 to the first, which is just 1x. So this whole thing just becomes 1x. Plus, this is going to be, again, a 1 over 2 factorial is just 2. X minus 0 squared is just x squared. Same thing for this one. For the third, we said we got 1. 3 times 2 times 1 is 6. X minus 0 to the third is x to the third. This is just 1x, so if you want, you can just write it as x. That's fine. If that doesn't make sense, let me know. Next, let's do the same thing for the function sine of x. Well, the derivative of sine is cosine. The second derivative is the derivative of cosine, which is negative sine. The third derivative is the derivative of negative sine, which is negative cosine. Plug 0 in. Sine of 0 is 0. Cosine of 0 is 1. For the second derivative, negative sine of 0 is 0. And then negative cosine of 0 is negative 1. So when I'm doing P3, so the first part is just going to be the function at 0, which we said was equal to 0. So I don't even need my first term. My next one's going to be 1 over 1, which is just 1, times x minus a to the first. My a is equal to 0, so it's just x to the first, which is just an x. For my next term, 0 is what I got, so my next term, I don't even need it, because that's what I'll have up top, so it's going to cancel everything else out. Then for my last term, I get negative 1 over, since this is n equal to 3, I would do 3 times 2 times 1, which is over 6. X minus 0 to the third is x to the third. So that's what I get there. Then for part C, they want us to do cosine. So do the same thing for cosine. F of x is going to be the cosine, which we already did. First derivative, the derivative of cosine is negative sine. Second derivative, the derivative of negative sine is negative cosine. Third derivative, the derivative of negative cosine is negative sine, which would make it positive sine. So again, I forgot to circle this. So again, plug in 0. Cosine of 0 is 1. Plug in 0 to the derivative. negative sine of 0 is 0. For the second derivative, negative cosine of 0 is negative 1. For the third derivative, sine of 0 is again 0. So for the first one, when n is equal to 0, you get 1 over 1 times 1, so just 1. This term right here, 0 is what I get, so I'm good there. For this next one right here, negative 1 over, n is equal to 2 here, so it's 2 times 1, which is 2. X minus 0 squared is just x squared. And then for the last one, 0 is what I got, so I don't even need it. So that's what I get for P3 for cosine. If any of that doesn't make sense, please let me know, because I guarantee you, this is a huge hint, there is a question on the homework and there is a question on the final where you're gonna have to be able to do these. So if it does not make sense, please reach out and let me know. I'm actually gonna keep this because I'm gonna go back and use it in an example towards the end. So I'm gonna keep this. Let me know if that doesn't make any sense though. All right. Example number 4. Consider the function f of x equals the cube root of x. For part A, find the first and second Taylor polynomials for f at x equal to 8. So I want to use P1 and P2. This time I'm actually going to find both P1 and P2 because in part B it's going to say use these two to estimate the cube root of 11, and I want to show kind of what happens there with both of these. Okay, so part A, we're going to find P1 and P2 for the function cube root of x at x equal to 8. So for P1, I just need the first derivative. So let's start with the function, which is the cube root of x, which I'm going to write as x to the 1/3. The derivative of that, I can use the power rule. Bring the power down, gives you 1/3 x. Decrease that by 1, gives you negative 2/3. And then the second derivative, which I'm going to need for P2, so I'm going to go ahead and find it here. Again, bring the power down, negative 1/3 times 2/3 is 2/9 x. Again, decrease that by 1, gives you negative 5/3. So now let's plug in 8. 8 to the 1/3 is saying the cube root of 8, which is 2. First derivative at 8. 8 to the negative 2/3. What this means is first, the 3 on the bottom means I'm doing the cube root. The cube root of 8 is 2. So now it's 2 to the negative 2. 2 to the negative 2 is like saying 1 over 2 squared, which is 1 over 4. So 8 to the negative 2/3 is 1 over 4. 1 over 4 times 1 over 3 is 1 over 12. Then do the same thing for the second derivative. 8 to the negative 5/3. Again, the cube root of 8 is 2. So what I really want is 2 to the negative 5th. That's 1 over 2 to the 5th. 2 times 2 times 2 times 2 times 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times another 2 is 32. 1 over 32 times negative 2/9. Negative 2/9 times 1 over 32. 2 and 32 can cancel to give me 16. 16 times 9 is 144. So negative 1 over 144. So for P1, I just want my first two. I just want these. Okay. So for P1, remember I always start with just f at 8. F at 8 is 2, so it's just 2. Plus what I got right here, which is 1 over 12, over 1 factorial, which is just 1. So I'm just going to rewrite it as 1 over 12. Times x minus a, which is x minus 8, to the first. So I'm just going to leave it there. That is P1. For P2, it's the same thing. It's going to start with the same two terms. I'm just going to add a third term. So remember, this is where n equals 2. So what I got was negative 1 over 144. 1 over 144 over 2 times 1, which is 2, times x minus a, which is 8, squared. 1 over 144 divided by 2, I can do 144 times 2, which is 288. So this is going to give me 1 over 288 times x minus 8 squared. So that's what I get for P1 and P2. If it doesn't make sense, let me know, please, and I will help you out. So part B says we're going to use those to estimate cube root of 11. So using P1, the cube root of 11 is about 2 plus 1 over 12, 11 minus 8. 11 minus 8 is 3, so 2 plus 1 over 12 times 3. 1/12 times 3. 3 over 12 is 1/4, so 2 plus 1/4. 2 plus 1/4 is going to be 9/4. So using P1, the cube root is about 9/4. Now let's use P2. Oh, and 9/4 is 2.25, if that's how you want to use it. Using P2, the cube root of 11 is about, so starts the same way, 2 plus 1/12, 11 minus 8, but I'm going to include minus 1 over 288, 11 minus 8 squared. Now, this part over here, we already know that's what we did on our last step. That's 9 over 4. So this is 9 over 4 for all of this. So now I just got to worry about this. 11 minus 8 is 3. 3 squared is 9. So I'm doing minus 9 over 288. Get a common denominator there. I think 288 is divisible by 4. It is. That's so helpful. So I need 288. To get that, to get to 288, I have to do times 72. 9 times 72 is 648. So 648 over 288 minus 9 over 288 is 639 over 288, which, if you divide that, is about 2.21875. So notice these are pretty close. Think about it really quick. Which one which one does grammar? Which one do all of you guys think is the closest? Think a little bit about it. Which one would you think is the closest one? Well, it would make sense P2 would be the closest one because there are more terms right here, right? I made it as specific as I possibly can. I'm adding more terms. So P3 would be even closer. P4 even closer. Just to show you, if I actually did the cube root of 11, I'm going to do the cube root of it, 2.22. This one is in fact the closest one. So, and then again, if I did P3, it would be even closer, and so on and so forth. Example number 5 is doing the same thing. Do the same as example 4 with the function f of x equals the square root of x at x equal to 4. We're going to just find P1 and P2. So example number 5, we're going to find P1 and P2 for the function square root of x at x equals 4. All right, so P1 and P2. P1 means I only need f prime, but P2 means I need f2 prime, so let's go ahead and go that far. F of x square root of x. The derivative of that is 1 over 2 square roots of x. And the derivative of 1 over 2 square roots of x, you could do that as 1 over 2x to the 1/2, which is 1/2 x to the negative 1/2. Taking the derivative of that, bring the power to down front, that gives me negative 1/4 x. Decrease this by 1, negative 3/2. So negative 1/4 x to the negative 3/2. I'm doing it at x equal to 4, so f of 4 is going to be the square root of 4. Square root of 4 is 2. 1 over 2 square root of 4. Again, the square root of 4 is 2. 2 times 2 is 4. So this is 1 over 4. Plug in a 4 right here. Again, the over 2 means I'm doing the square root. Square root of 4 is 2. 2 to the negative third is like 1 over 2 to the third, which is 1/8. 1/8 times negative 1/4 is negative 1 over 32. So for P1, again, remember all of our terms are the nth derivative at a, n factorial, x minus a to the n. For n equals 0, it's just whatever I got here, so that would just be 2. And then for n equals 1, it would be what I got right here over 1, so that's just 1/4, x minus a, which is x minus 4 to the first. So I can just stop right there. We are good with that. P2 is going to start the same way because the first two terms are the same. But I'm going to add another term, negative 1 over 32 on top over 2 times 1, which is 2. Negative 1 over 32 over 2 is negative 1 over 64. X minus a, we already said a was 4 to the power of 2. So these would be helpful if I wanted to find the square root of something close to 4. So like this would be helpful in finding the square root of 5 or the square root of 3, right? But this wouldn't be very helpful in finding like the square root of 15 because 15 is too far away from 4 for this to really help us out. You know what I mean? If that doesn't make sense, then let me know. Example number 6. Find the Taylor series for the function f of x equals 1 over x at x is equal to 1. So we're finding the Taylor series here. Notice it did not say find the first 4 terms, find the first 5 terms. It just wants to know what the series is. So I'm going to see if there's a pattern we can find in all of this stuff. So I'm going to do as many derivatives as I can to see if it kind of helps us out. So let's do 4 of them. So the function is 1 over x. The first derivative, negative 1 over x squared. Second derivative is 2 over x cubed. The third derivative is negative 6 over x to the fourth. The fourth derivative is going to be 24 over x to the fifth. Make sure you know how to get those. I used the power rule. So evaluate all those at 1. 1 over 1 is just 1. 1 squared is 1. 1 over 1 is 1, so negative 1. 1 cubed is 1. 2 over 1 is 2. 1 to the fourth is 1. 6 over 1 is 1, so negative 6. And then the fourth derivative, 1 to the fifth is 1. 24 over 1 is 24. So let's list out as many terms as I can. So remember, on all of these, it's the nth derivative at a over n factorial x minus a to the n. A here is 1. So for n equal to 0, that's just the function value minus, because it's a minus sign right here, negative 1 over 1 factorial is just a 1. 1 over 1 is just 1. x minus a to the first is just x minus a, and our a is 1, so x minus 1. Next one is 2 over 2 factorial. 2 times 1 is just 2, so this becomes 2 over 2, which is just 1 times x minus a squared, minus, I would have a 6 on top, but down here I do 3 times 2 times 1, which is also 6. 6 over 6 is just 1, so this would just be x minus a to the third, like that. Then for the next one, it would be plus 24 on top. Down here, it would be 4 times 3 times 2 times 1. 4 times 3 is 12. 12 times 2 is 24. 24 over 24 is 1. So x minus 1 to the fourth. And so from here, we can see what the pattern is. Then it would be minus x minus 1 to the fifth plus x minus 1 to the sixth, on, like that. And it would just keep going and going forever and ever and ever. All right. We are actually not going to worry about examples 7 and 8 for the purposes of my class. So we can go ahead and ignore those and move straight on to example number 9. This is something that is very important. It is extremely important you know how to do this. So if it does not make sense, please ask me because it is important, okay? Use the Maclaurin series expansion of e to the ix to prove e to the ix is equal to cosine of x plus I sine of x. This is a mathematical rule that is used a bunch, and we are going to prove it now, okay? We are going to prove it here using everything we just have learned. So we're going to use the Maclaurin expansion of e to the ix. So remember, Maclaurin means a is equal to 0. So I want to use a is equal to 0 for the function e to the ix. So I want to do as many terms as I possibly can. I really want to do a bunch of terms. Let's do up to f5 prime. Okay. So first start with f of x. The function is just e to the ix. The derivative, remember, we know our whole thing is that e stays e, but I have e to the ix. So by the chain rule, I need to times this by the derivative of ix. I is just a constant, so the derivative of ix is just I. So this derivative is I e to the ix. Again, by the chain rule. If that doesn't make sense, make sure you understand that. You can ask me or whatever. So the second derivative, I would do the same thing, right? I is a constant, so I don't need like the like product rule here. But I would do the same thing, e stays e, but I need to times this by I. So out front, I would end up with I squared e to the ix. Well, what is I squared? I squared, remember the whole point of I is I is equal to the square root of -1. So I squared would be square that, -1. So this is negative e to the ix. Then the third derivative, do the same thing, e stays e, but I need to bring down an I, so negative I e to the ix. The fourth derivative, again, I would bring down another I, so it would be negative I squared. We already said I squared was equal to -1. So negative the -1 would be positive 1 e to the ix. And notice I'm back to what I had to start with. So when I took the fifth derivative, I would just start back over. I e to the ix. For the sixth derivative, I would do it again. My next one was negative e to the ix, and it would just keep going on and on. So the Maclaurin series for e to the ix tells me, so my first term, I have to plug in the 0, forgot to do that. e to the power of 0 is equal to 1. Same thing here, I would get I times 1, which is this I. E to the 0 is equal to 1, so that's going to be negative 1. This would give me negative I, and then it would cycle back over. 1, this is a 4. The fourth derivative, the fifth derivative, just be I. The sixth derivative would be negative 1, and on and on. So expanding the Maclaurin series of this tells me that f of x is about, for the first term, remember we always just keep what it was, so 1. I'll write it down again, but fn at 0 over n factorial. X minus 0 to the n, so that's just x to the n. So for n equals 1, I would get I over 1, so that's just I, x to the first, so plus ix, minus 1 over, and this is a 2, so 2 times 1 is 2, so minus 1 over 2, x squared, minus I over 3 times 2 times 1 is 6, right? So minus I over 6, x to the third. And then 1, 2, 3, 4, 1, 2, 3, 4. Okay, so now I'm right here. 1 divided by 4 times 3 times 2 times 1 is 24. X to the fourth. Plus I over 5 times 4 times 3 times 2 times 1 is 120. X to the fifth. Minus 1 over, times that by 6 gives you 720. X to the sixth, and it would keep going. Let's see if I can rewrite this. Notice some of these terms have an I, some of them don't, right? So let's group up every term without I, and then group up every term with I. See, because this one, it doesn't have an I. This one, it doesn't have an I. This one, and then some of them do. So let's group them up. So the terms without I is going to be 1 minus 1/2 x squared plus 1 over 24x to the fourth minus 1 over 720 x to the sixth, on and on. And then every term with I, I'm actually going to factor it out, because everything with an I, this would just be an x minus 1/6 x to the third plus 1 over 20 x to the fifth, and it would keep going on and on. Well, what do y'all notice about that? This is why I kept this board over here from example number 3, because if you notice, 1 minus 1/2 x squared plus 1 over 24x to the fourth minus 720x to the sixth, blah, blah, blah. That's what I got right here for cosine. This is cosine of x. This whole thing right here is cosine. What do you notice about this? Well, look at that. That's what I got for the sine of x. That's sine of x. This is sine of x. So what I end up with is cosine of x plus I sine of x, which is what we needed to prove. So we're good there. Like I said, this is an important skill, so if it doesn't make sense, let me know. In fact, if anything we have done so far, anything throughout all Cal 2 does not make sense, please let me know. I will be happy to help out.